Every day, billions of people rely on products made from crude oil without ever realizing the extraordinary engineering required to obtain it. The gasoline that powers cars, the diesel used by trucks, the jet fuel that keeps aircraft in the sky, and even many plastics, medicines, and everyday household items all begin deep beneath the Earth's surface. Hidden several kilometers underground are vast reservoirs of oil trapped inside layers of solid rock that formed millions of years ago. Reaching these reserves is one of the greatest engineering challenges ever accomplished by humanity. Modern oil drilling combines geology, mechanical engineering, advanced electronics, high-strength materials, and powerful machinery to drill deeper than many mountains are tall. Every well requires months of planning, thousands of tons of equipment, and a highly skilled team working around the clock to safely reach underground energy reserves. Long before any drilling begins, scientists must first determine where oil might be located. Geologists spend years studying rock formations, ancient seabeds, and underground structures that were formed millions of years ago. Today, oil exploration relies heavily on seismic surveys, one of the most advanced techniques used in the energy industry. Powerful vibration trucks on land or specialized ships at sea send controlled sound waves deep into the earth. As these waves travel through different rock layers, they bounce back towards sensitive recording instruments. Computers analyze millions of these returning signals to create highly detailed three-dimensional maps of the underground. These digital images allow geologists to identify structures where oil and natural gas may have accumulated over geological time. Finding oil underground is only the beginning. Before drilling can start, engineers conduct detailed environmental studies, soil testing, and geological analysis to ensure the location is suitable for safe operations. Roads must often be built to transport heavy equipment to remote drilling sites, while temporary facilities are constructed to support workers and machinery. Every drilling location requires electrical systems, water supplies, fuel storage, communication equipment, and strict safety infrastructure before the first drill bit ever touches the ground. At the center of every drilling site stands the drilling rig, a massive engineering structure designed to support the enormous weight of drilling equipment. Depending on the depth of the well, a drilling rig can stand more than 50 meters tall and weigh thousands of tons. The tallest part of the rig is called the derrick, a towering steel framework that supports the drilling system. Inside the derrick, powerful hoisting equipment repeatedly raises and lowers sections of drill pipe that are connected together to form an extremely long drill string capable of reaching several kilometers beneath the Earth's surface. At the bottom of the drill string is one of the most important tools in the entire operation, the drill bit. Although it may appear relatively small compared to the size of the rig, the drill bit performs one of the toughest jobs in engineering. Modern drill bits are manufactured using extremely durable materials such as tungsten carbide and industrial diamonds, capable of cutting through some of the hardest rocks found underground. As the drill string rotates, the bit grinds, crushes, and cuts its way through layers of soil, sandstone, limestone, shale, granite, and other geological formations that have remained untouched for millions of years. Powering this drilling operation requires enormous amounts of energy. Massive diesel engines or electric motors drive sophisticated mechanical systems that rotate the drill string with tremendous force. Modern top drive systems allow engineers to rotate thousands of meters of drill pipe smoothly while carefully controlling drilling speed, torque, and downward pressure. Every adjustment is monitored continuously because even small changes in drilling conditions can significantly affect performance, equipment wear, and overall safety. As drilling continues deeper underground, conditions become far more challenging. Temperatures steadily increase due to the Earth's natural geothermal heat, while underground pressures rise dramatically. At depths of several kilometers, temperatures can exceed 150 degrees Celsius, and the surrounding rock exerts tremendous pressure on the wellbore. Without careful engineering, these extreme conditions could damage equipment or cause dangerous well failures. This is why every stage of drilling is carefully planned and continuously monitored by experienced engineers. One of the most important systems used during drilling is drilling mud, often referred to as drilling fluid. Despite its name, this is far more than ordinary mud. It is a carefully engineered mixture containing water or oil, specialized clays, chemicals, weighting materials, and performance additives designed for specific drilling conditions. Powerful pumps continuously circulate this fluid from the surface down through the drill pipe and back up the outside of the well. This constant circulation performs several critical functions simultaneously. First, the drilling fluid cools the drill bit, preventing excessive heat from damaging its cutting surfaces. Second, it lubricates moving parts, reducing friction between the drill string and surrounding rock. Third, it carries crushed rock fragments, known as drill cuttings, back to the surface where they are removed before the fluid is reused. Most importantly, the drilling fluid balances underground pressure inside the well. By carefully controlling the density of the fluid, engineers prevent oil, natural gas, or underground water from unexpectedly rushing into the well, greatly improving operational safety. At regular intervals during drilling, sections of steel casing are installed inside the well. These thick steel pipes strengthen the wellbore and prevent surrounding rock formations from collapsing. After each casing section is lowered into place, cement is pumped into the space between the casing and the surrounding rock. This cement hardens into a strong protective barrier that seals off underground water sources, isolates different geological formations, and provides long-term structural stability. Multiple layers of casing and cement are typically installed as the well becomes deeper, creating several independent safety barriers. Drilling engineers constantly collect information from deep underground using sophisticated measurement tools located near the drill bit. These systems measure direction, temperature, pressure, rock density, vibration, and many other properties while drilling is still in progress. Instead of waiting until drilling is complete, engineers receive valuable information in real time, allowing them to adjust drilling operations immediately. This technology, known as measurement while drilling and logging while drilling, has revolutionized modern oil exploration by greatly improving drilling accuracy and reducing unnecessary costs. Contrary to what many people imagine, modern wells are rarely drilled straight downward for their entire length. Directional drilling technology allows engineers to gradually steer the drill bit through underground rock formations with remarkable precision. Using adjustable drilling tools, powerful downhole motors, gyroscopic navigation systems, and computer guidance, a well can curve horizontally for several kilometers after reaching the desired depth. This allows multiple wells to reach different parts of the same reservoir from a single drilling location, reducing both environmental impact and construction cost. Eventually, the drill bit reaches the oil-bearing reservoir. However, drilling does not end immediately. Engineers first evaluate the reservoir using advanced logging instruments lowered into the well. These tools measure electrical resistance, natural radioactivity, pressure, porosity, permeability, and fluid content within the surrounding rock. By analyzing this information, geologists estimate how much recoverable oil is present and determine whether the well will produce economically over many years. Once the reservoir has been fully evaluated, the production stage begins. Special perforating tools create small openings through the steel casing and surrounding cement directly into the oil-bearing rock. These perforations allow crude oil and natural gas to flow into the production tubing installed inside the well. In some reservoirs, natural underground pressure is strong enough to push oil to the surface without assistance. In others, artificial lift systems, such as pump jacks, electric submersible pumps, or gas lift systems, are installed to maintain steady production as reservoir pressure gradually declines. Modern drilling operations rely heavily on advanced automation. Thousands of electronic sensors continuously monitor drilling speed, equipment vibration, fluid pressure, temperature, torque, and well conditions. All of this information is transmitted instantly to computerized control systems where engineers can monitor every aspect of the operation in real time. Artificial intelligence is increasingly being used to predict equipment failures, optimize drilling performance, and improve operational efficiency while reducing costs and minimizing environmental risks. Safety remains the highest priority throughout every drilling operation. One of the most important safety devices is the blowout preventer, commonly known as the BOP. Installed directly above the well, this enormous hydraulic system is designed to seal the well instantly if dangerous underground pressure suddenly increases. Multiple layers of emergency shutdown systems, pressure monitoring equipment, fire protection systems, gas detection sensors, and backup power supplies ensure drilling operations remain as safe as possible under even the most demanding conditions. Environmental protection has also become a major focus of modern oil drilling. Companies now use closed-loop drilling systems that recycle drilling fluids, reduce waste, and minimize contamination. Advanced spill prevention equipment, groundwater protection measures, emission control technologies, and continuous environmental monitoring help reduce the impact of drilling activities. In many locations, restored drilling sites are carefully rehabilitated after operations are completed, allowing the surrounding environment to recover over time. Technology continues to transform the oil industry. Automated drilling rigs, robotic pipe handling systems, artificial intelligence, advanced data analytics, and remote operations centers are making drilling safer, faster, and more efficient than ever before. Engineers are also developing smarter drill bits, stronger materials, and more accurate underground imaging systems capable of reaching reservoirs that were once considered impossible to access. These innovations continue to push the limits of what modern drilling technology can achieve. Although drilling several kilometers beneath the Earth's surface may appear almost impossible, it has become a carefully controlled process made possible through decades of engineering innovation. Every successful well represents the combined efforts of geologists, drilling engineers, mechanical specialists, computer scientists, safety experts, and thousands of skilled workers who coordinate every stage of the operation with extraordinary precision. From advanced seismic exploration and precision drilling to intelligent automation and multiple safety systems, modern oil drilling stands as one of humanity's greatest engineering achievements, making it possible to unlock the energy resources hidden deep beneath the Earth and deliver them safely to the world every single day.